Hello everyone, and here's a Physics 30 from Lesson 2 from our class notes. Again, this is a recap of the Physics 20 concepts, but very important coming into Physics 30 because these concepts will be used in some of the more high mental activity types of questions that you'll see. Here we go, Lesson 2, this is dynamics. So we're looking at all the different forces, and of course we need to be referencing our Newton's 3 laws. Of course, Newton's first law is that an object will remain at a constant velocity or uniform motion until a force is exerted upon it. So the object continues due to inertia. Newton's second law is that if there is an unbalanced force, the object will accelerate in the same direction as the force net. Okay, this F net. And we should be getting pretty good now, and we'll be doing quite a bit of this as we move through this F net expression. So you just add up all the forces, and then if you have an unbalanced force, you can go ahead and call that a mass times acceleration. Okay, and then Newton's third law, this is for every action there is an equal and opposite reaction. This is a big one in momentum in Unit 1 in Physics 30. That we like to test this quite a bit. The diploma likes to test this. It's kind of a misconception that we can go after. Doesn't matter the size of the objects. If they're exerting forces on each other, then the force is going to be the same. So, for example, the force that you yourself have with regards to the planet Earth, they are going to be equal and opposite. So the force that you're experiencing being pulled towards the surface of the Earth, there is an equal and opposite force whereby the Earth is pulled towards you, even though we don't really think about that because, of course, the mass of the Earth is hugely greater than the mass of you, and therefore the force itself is insignificant on the inertia of the Earth. But it's true, it's there. More realistic would be if you had two cars or a car and a truck in a collision, and if we were to look at as they collide, if we were to look at the forces, the force exerted on the truck by the car is going to be exactly the same magnitude as the force exerted on the car by the truck, and vice versa. So we'll be keeping an eye on this idea as we move through momentum. Look out for this. Anyway, here's example number 1. Couple of key skills going on here. We're going to keep track of these key skills. We definitely are going to want to do our F nets. That's a key skill that we're going to need to be getting good at. We're also going to be doing our FBDs, our free body diagrams, and that's another big one that we need to get quite good at. So here we go with our first example question. You have a 1,700 kilogram car traveling right at a constant speed of 20 meters per second. It experiences a propulsive force of 8,000 newtons. Okay, so that's obviously going to be going in the same direction as the motion. And then there's also a frictional force of 3,000 newtons. And that's obviously going to be going in the opposite direction to the direction of motion. So we need to now determine the air resistance force. So let's just get ourselves a free body diagram going here, and then we can hopefully analyze the different forces. Okay, so here's my car. I'm going to do a little schematic of a car. Here it is. We know the mass, so we might as well write this in here. The mass is 1,700. We know it's going at a uniform motion. It's going at a constant speed. So just keep in the back of your mind, this is a physics principle 0. Okay, this is a balanced force. This is going to be an F net of 0. Physics principle 0 means the F net is balanced. So we just want to keep that in the back of our minds because this is an important thing to think about whenever we're doing any physics problems. We want to think about the physics principles because this determines how we analyze it. Okay, so let's start thinking about the forces. Oh, actually, I'm going to put the speed on as well. So the speed of this is constant and it's 20 meters per second. I'm going to say it's this way. Okay, forces. Well, to keep a car going at a constant speed, you need a force. That's why the car uses gas as it's traveling on a highway. So there's my propulsive force. I'm going to say that this is the force applied by the engine. Okay, and then there's going to be a force of friction that's going to be coming this way against it. So this here is going to be the force of friction. And I'm also going to have this air resistive force. So there's going to be another force. Okay, and so I've got the force of friction and I've got the force of air resistance. Okay, now this is key. I'm going to do my Fnet expression. I'm going to write it out. Fnet is the sum of all forces, however many there are. And so I can say that I'm going to treat this side to be, this side is going to be positive, this side is going to be negative. So I'm going to say that there is a force applied by the engine. There's also going to be a force of friction. And there's also going to be a force of air resistance. Okay. Now, can I say that my Fnet becomes an accelerated force? Well, this is the key. Can I do it? No, I can't. My acceleration is going to be 0. Okay, and that's really important. That means that my acceleration being 0 means that this is going to be 0, which means when I add all these forces together, when I add my force applied, my force of friction, and my force of air resistance, these need to equal 0. And you can probably tell just by looking at the vector the free body diagram, that this force over here, this force applied, this is going to be equal to both of these arrows, because this free body diagram needs to be balanced. And if I went ahead and put in my negative signs, you can probably even see that. Okay, so I'm going to have a negative force of friction and a negative force of air resistance. And that tells me that, if I was to write this out, I can bring these over here. My force of air resistance plus my force of friction is going to be equal to the force applied. Okay, and I have these values available. The force applied is given. It's 8,000 newtons or 8 kilonewtons. I'm going to write that out as 8,000 newtons. And the frictional force is given as 3,000 newtons. So the force of air resistance plus 3,000 newtons is equal to this force applied of 8,000. So a little bit of arithmetic here. The force of air resistance is going to be 8,000 newtons minus 3,000 newtons. So that's 5,000 newtons. Now I just have to say which way it's going. Well, it's going to the negative side, and I'm going to say that's the left of the page. Okay, so the force of air resistance is 5,000 newtons to the left of the page. Okay, example number 2. Now we have a rocket, so I'm going to go ahead and draw this out. Here's my rocket. There's going to be some boosters at the bottom. There's my thrusters. And I'm going to do my FBD, my free body diagram, keeping all my forces on here. So I've got a 1,400 kilogram rocket. It's got an upwards acceleration, so I might as well put that on here. There's an acceleration. Okay, now this gets me thinking about my physics principle, and so hopefully you are too. Physics principle here is going to be number 1. This is where the Fnet does not equal 0. Okay, so I'm thinking about this. My Fnet does not equal 0, which means I have an acceleration. I'm going to have an unbalanced free body diagram, which means my Fnet expression is going to give me an ma. I can say Fnet is equal to ma. Let's keep going with our forces. There's my acceleration upwards. That means I'm going to have some kind of applied force. This is going to be coming from the thrusters. This is actually what I'm trying to find. Okay, it's asking me to determine the propulsive force. I've got an acceleration upwards of 27 meters per second squared. And I'm told that the force of the force of air resistance, the FAR, is 11,000 newtons. Okay, so let's put this on here too. This is my FAR, and that's 11,000 newtons. Okay, one other force we haven't identified, and there's an assumption here. Of course, this rocket is on planet Earth. And so if we're sat on planet Earth, we can go ahead and assume that there's a force of gravity as well. So I need to make sure I put that on there. There's another vector here, and it's FG. Okay, so I think we're ready to do our Fnet expression. I think I've taken care of all of the forces. So my Fnet, again, is the sum of all of the forces. I'm going to add them all up. And so I'm just going to list them off here. I'm going to say force applied plus force of air resistance plus force of gravity. And of course, now we can think about our physics principle. This Fnet is going to become our mass times acceleration. Okay. And just to keep track of things, of course, I'm going to say up is positive, down is negative. And so I can start thinking about how these positives and negatives play into it. Let's just identify a couple of the negatives. This one's going to be a negative, and this one's going to be a negative. Okay, let's put some numbers in because I know the mass as well. Should have probably put that in initially. The mass here is 1,400 kilograms. So I can abbreviate some of these forces now. I'm going to say that MA, so mass times the acceleration of the system, is going to be the force applied, okay, which is what I'm trying to work out, that's my question mark, plus the force of air resistance. Well, I'm given that, so I'm just going to go ahead and put that in, keeping track of this as a negative. This is going to be a negative 11,000 newtons, plus, and now I have my Fg, my force of gravity coming down. Well, Fg is equivalent to mg. So let's go ahead and put that in, mg. But that's also going down, so that's going to be a negative as well. All right, so once I've got my statements in place and I've kept track of my negatives, which is really important, and that's why doing an FBD is crucial, so you can really see where these positives and negatives are. Once I've got these negatives in place and I've written out my Fnet expression, now it's just a case of plugging in the values, keeping those negatives in place, and at this point I'm pretty close to solving it, so I'm just going to keep going. Hopefully you can see now that the force applied by the thrusters is going to be equal to 37800 newtons plus the 11,000 newtons from air resistance plus the 13,734 newtons from the force of gravity, and that's going to give me 6.25 times 10 to the 4 newtons. Okay, so the propulsive force of the thrusters is 6.25 times 10 to the 4 newtons, and of course this is upwards.